Well, it's natural to assume that mathematics comes from physical reality. And in fact, a lot of things that we do in mathematics have roots in nature. For example, numbers, 1, 2, 3, 4, 5. Obviously, we count on our fingers. And that's how we come to first get acquainted with numbers. But there are many concepts in modern mathematics which do not manifest themselves in physical reality in any obvious sense. It may happen sometimes that mathematics which is developed purely within the narrative of the subject then later finds applications. But initially, when mathematicians work on them, when mathematicians develop these ideas, oftentimes they don't have any expectations that these ideas, these theories, will actually find real-world applications. And one example that I like is this theory of curved shapes, the so-called Riemannian geometry, which was developed by a German mathematician, Bernhard Riemann, in the second half of the 19th century. And his idea was to develop this most general theory of shapes such as a sphere or the torus, the surface of a donut, and things like that. And why was he doing that? He was driven by some intrinsically mathematical problems. He didn't expect that our world would actually be non-Euclidean. And yet that's what physicists then later told us. Albert Einstein, 60 years later, in his general relativity theory, used Riemannian geometry to describe space and time and to show that space and time is not flat and Euclidean as humans believed for millennia, but actually is curved. A ray of light doesn't travel along a straight line, but is bent around a massive object like a star. This is something which was experimentally verified. And to be able to speak about such spaces, such curved spaces, one needs this mathematical theory. And that mathematical theory was developed 60 years earlier without any expectations like that. So that's what Eugene Wigner, I think, was referring to when he was talking about this almost unreasonable, how unreasonably good, how unreasonably effective mathematics is in the description of natural science. And I think it's still an open question. Likewise, in quantum mechanics, we use complex numbers, things which were discovered by mathematicians who tried to solve problems of a totally different nature. They tried to solve algebraic equations where solutions could not be found in real numbers. But then, now, complex numbers are bread and butter of quantum physics. So what does it mean? What does it tell us about the world and about us? I think the jury's still out on this, but it's a fascinating question.